Hello everybody, so this is the second video associated with chapter 2 of the reinforcement learning course. So in the previous video we discussed the K-armed bandit problem where you had a sequence of steps or plays, and on each play you had to pull some lever and you received a reward whose distribution is associated with the lever, and the objective was to maximize over the set of all plays your expected reward you were obtaining. So several topics were discussed. Among them, one was to how to form estimates of the expected reward for each of the various levers. Okay, so we had this definition earlier that QTA was the estimated expected reward associated with lever A or action A right before the teeth play is performed. Okay, so we had the following definition. So this estimate of the value of action A was simply obtained by averaging the your reward, all rewards obtained from lever A in all previous plays. So in all plays up until play T minus 1. And if that lever was never sampled from, then you can assign an initial estimate of 0 for that lever. Okay, so if this is the formula we proposed earlier for the estimation of the expected reward for lever A from information gathered from the first T minus 1 place. Okay, so if you want to directly use that formula, this would entail that you need to store all the rewards R1, R2, R3 until RT minus 1. So all these rewards appear in this formula, and you also need to store all actions previously taken at all steps. So A1, A2, A3, A4, etc. Okay, so in reinforcement learning, we said we typically apply a sophisticated approach of trial and error to try to learn. Well, the idea is to have many trials. Okay, so to for example act repeatedly with your environment to learn, and we for that reason we expect to have many trials to act repeatedly a large number of times. And if this is the case, then the number of rewards and the set of all past actions might be too long to store. Okay, so we're gonna show a recursive formula which would prevent the need to store all previous actions and rewards and still obtain estimates of the expected value of all actions. Okay, so here a bit of definition. NTA is defined as here the sum across all first T minus 1 plays of an indicator variable, which is 1 if the ith play, the action for the ith play was A, so the 8th lever was pulled on play I. So NTA is simply the number of times action A was taken up until time T minus 1. So here, we're gonna assume that if the action A was sampled at least 1 by time T minus 1, so if this is the case, then we can obtain a recursive formulation of the expected, the estimated expected value for action A. Okay, the expected value of the reward for action A. Okay, so here QT minus 1, T plus 1A. So here this is simply applying the definition of QT plus 1A. So it's the sum of all rewards until play T, where if action A was taken, and the denominator here is simply the number of times action A was taken up until time T. So this is going from here to here. It's just the definition of Q. And then to go from here to here, we can simply break the summation above. So this sum up until time T, it can be expressed as the last term, so the time T term, and the sum of all terms until t minus 1. So we can break the summation into two. And here, this sum of indicators, we said it's the number of times action A was sampled by time t. So by definition, this is simply nt plus 1a. Okay, so the same quantity here and here. This is just the denominator here. Okay, and here, uh, if we take the definition, okay, maybe I'll write this. So here the definition of QTA, so QTA was equal to sum over all I goes from 1 to t minus 1 of the indicator. I won't write this, but just for convenience, but this is this index times Ri divided by, this is NTA. Okay, so what we can do here, we can take this NTA, throw it on the other side here. So we obtain that the sum of indicators times reward up until time t minus 1 is equal to NTA times QTA. Okay, so this comes from the definition of QTA. And then it's good because we now have a recursive formula, so we can obtain qt plus 1a from qta. And here what we need is the following quantities. We need to know nta, and here we need to know the reward at time t and the action at time t. Okay, so if we know all these quantities, we can know qta plus 1. We don't need to keep track of all previous rewards. Okay, so what keep tracks of all previous rewards is QTA. So this is the quantity we need to store if we want to be able to know QT plus 1A. Okay, so let's rewrite this a bit. So, okay, so here there are two possibilities. Maybe I'll write them here. Possibility 1 is, let's say, A T is equal to A. Okay, so if at play T, the action A is selected, then this entails that QT plus 1A is equal to, here this first term here, it will become simply RT divided by NT plus 1. So this is plus NT QT, so over, sorry, this is N and T plus 1. And furthermore, we have, since action A was selected, in that case we have NT plus 1, plus 1A is equal to NTA plus 1. Okay, so we could plug this relationship in here, and if we do that, then we obtain that, maybe I'll write it here, this guy becomes equal to RT plus NT. So here this is NTA, but just to be more convenient, sorry, this doesn't write well, so I'll try to be a bit more succinct. Divided by QT divided this whole thing by NT plus 1 plus 1 here. Okay, so if action A is selected, then the estimate of the expected reward for action A at time t plus 1 is the current reward plus the number of times the action A was sampled in the past times the expected reward estimated expected reward as of the previous step divided by here. Whoops, sorry, this should be, there should be no plus 1 here. This is just NT plus 1 here, like that. Okay, so here we can take this formula and plug it on the next slide. Sorry for that, it's a bit long. Okay, so we can take this expression and put it here. Okay, so we have that qt plus 1 can be two things. Okay, so if action A is selected by play T, this is the formula we just calculated. So your next estimate is your current reward plus the number of times action A was selected prior to play T times the previous expected value estimate divided by NTA plus 1. Okay, so this is if action A is selected. If action A is not selected, well, you don't have more new rewards from lever A, so your estimate of the action A simply remains unchanged. Okay, so you can take the previous formula in the previous slide, and you can verify that the previous slide's formula ends up being equal to QTA in that case. Okay, so here this first quantity, we can re-express it as this. Okay, so maybe it's easier to go from here to here than to from here to here. But here you can see that if you multiply this quantity above and below by NTA plus 1, the plus 1 cancels on top with this QA, and you re-obtain this formula. Okay, so here we have the following. This is QTA plus the current reward minus QTA divided by NT plus 1. So what this says is if we want to know the estimate of expected reward for action A after the Tth play, what you need to know is simply your previous estimate at the previous step plus your current reward. Okay, so you need to know your current reward, but this you observe it, minus your previous estimate divided by the number of times your previous action was action A was previously sampled plus 1. Okay, so the only quantities you need to track is QTA and NTA, and this is better because you don't need to store all previous actions and all previous rewards if you want to use this formula. Okay, so the only thing you need to store to apply the previous or this update formula for QTA, QT plus 1A is QTA and NTA. Okay, so this is requires much less memory if you want to apply it in practice. So whenever we take action A, we can just recall the previous formula. The previous formula has the following form. Okay, so when we take action A at play T, your action A estimate of the expected reward becomes your previous estimate from the previous step plus here some quantity, which we will call the step size, times the difference between your reward and your estimate of the expected reward. Okay, so this formula, it has the following form. It has the form new estimate here is equal to old estimate here, plus what we call the step size, times some adjustment, which is the target. The target is the quantity for which we want to estimate the expected value minus our old estimate. Okay, so this form here, we will encounter it repeatedly during the course. Okay, so what will change in the various algorithms we will encounter is the specification of the step size and the target. Okay, but this specific formula we will see this generic formula, sorry, we will encounter it over and over, so it's good to memorize it at this point. Okay, So in the previous expression, our step size, so here the step size it's nta plus 1, but in this case, if action A is selected, this is just nt plus 1a. So here the step size nt plus 1a shrinks through time. Okay, so as time goes by, this number here will become larger and larger because this is the number of times you've sampled from action A. Okay, so the step size in the previous formula decreases through time. Okay, if we use the sample average to estimate the expected rewards. Okay, so here and what happened before, we proposed to estimate the expected reward by an arithmetic average or equally weighted average of all previous rewards obtained from from action A. Okay, so here for this precise case, which is simply averaging rewards, the step size in this formula is 1 over nta plus 1, but we will see other algorithms which use different step size, and we will discuss their interpretation next. But in general, we can denote by alpha and a being the step. I've written time step, but this should be the step size. Okay, the step size to update your estimate of action A's expected reward at time t, at the nth time the action A is sampled. Okay, so in the previous algorithm, that step size had the form 1 over n. Okay, so here the previous algorithm we've outlined, it's the second case here. So when we weight all rewards equally to form our estimate of the expected reward, then this entails using a step size of 1 over n. So the nth time we obtain a new reward, then our step size becomes, for lever n, our step size is 1 over n in the formula. However, we will consider other possibilities in the previous formula. We will consider other schemes which entail weighting the previous rewards differently than having equal weights for all rewards. So it's possible to use what we call a constant step size to form our previous estimate, and in that case alpha and a would be equal to some constant alpha. Okay, so we could still apply I'll go back one slide. We could still apply this type of equation to form recursively estimates of the expected rewards for all actions, but then instead of using 1 over n as the step size, we could use other quantities. So one we will see next is to use a constant step size instead, and still apply this equation to form estimates of expected value of the various actions. Okay, so as we mentioned, the previous rule we discussed entails that all rewards are weighted equally. Okay, so to form the expected reward of an action A, you just have a equally weighted average of all previous rewards. So this is good in a stationary context, but if you have a non-stationary problem where rewards distribution varies slowly over time, then rewards you've obtained a long time ago, they become less relevant than the rewards you've received very recently. Okay, so in that case, to weight all rewards equally would not make as much sense than for stationary problems. Okay, so if you have a non-stationary problems where reward distributions vary and fluctuate through times, you might want to give more weights associated to give more weights to rewards received more recently. Okay, so we will see shortly that if we use a constant step size in the previous formula, so the formula in that case becomes new estimate of expected reward A is the previous estimate plus the constant step size times the reward, which is a target, minus the previous estimate. Then in this case, we're going to see this gives more weight to more recent rewards, and that might be better suited for non-stationary problems. Okay. So here we propose to use a constant step size, but and then we said that this entails weighing more recent rewards more highly. So this is what we're gonna show in the subsequent slides. Okay, so here a constant step size in the previous formula entails assigning exponentially decaying weights for reward. Okay, so recent rewards will have exponentially more weights than rewards received long ago. Okay, indeed, we can see that through the following recursion formula. So here, okay. So here, just let's go back one slide. This is the formula we've outlined when we have a constant step size here. But this formula, it can be rewritten by uh, combining this qt and this qt. So this can be rewritten as alpha rt plus 1 minus alpha qta. Okay, so we can see that the next estimate of action A is like a convex combination of the current reward and the previous estimate, okay, with factor alpha here. Okay, so we can apply here this rule in the following. We can consider it many times. So here, q t plus 1a. Okay, so before looking at the formula, just some quick definition. We're gonna assume that t1 until ts, are the time steps prior to t plus 1 where action A was taken. Okay, so we will only consider steps where action A was taken. So qt plus 1a is the number, the expected rewards estimated expected reward after t plays. And here from this definition here, this is alpha times the reward the last time the action A was selected, plus 1 minus alpha times the estimated expected reward the last time action A was selected. And we can apply the following formula, the previous formula, recursively. Okay, so this QTSA, let's write it, QTSA, this is an S here, this is equal to alpha R T S minus 1 plus 1 minus alpha Q T S minus 1A. Okay, so if we apply this equation, this recursive formula here, sorry, this is a bad parenthesis. Okay, so if we apply this formula, we can substitute here this QTS by alpha RTS minus 1 plus 1 minus alpha QTS minus 1 also. And then we can repeat that step. QTS minus 1, we can replace S by S minus 1 here in this recursion to express this guy in terms of QTS minus 2, etc. And continue like that up until we have the following equation, which is alpha times the sum across all previous steps where action A was taken, of 1 minus alpha to the power j times the previous rewards associated with action A at all previous steps action A was sampled, plus finally there's always this trailing term here, which eventually ends up being equal to Q1A, which is the initial estimate associated with action A, times 1 minus alpha to the power S. Okay, so this is the number of times action A was sampled prior to time t. Okay, So we can see here that if we apply a constant time step in the previous recursion formula, then the current estimate of the expected reward for action A is a linear combination of previous rewards obtained from action A. But here the weights, they're not constant. We can see that they're exponentially decreasing with the number of times the action A was selected. Okay, so the most recent reward has a weight alpha. The second most recent reward from lever A has a weight alpha times 1 minus alpha. So we multiply by 1 minus alpha. Uh, Third most recent reward times 1 minus alpha 2. Fourth most recent reward times 1 minus alpha to the power 3, etc. Okay, so we can see that more recent rewards from lever A have exponentially more weight than rewards obtained long ago. Okay, and plus this trailing term here, which depends on the initial estimate of action A. Okay, so here we have seen two possible choices for the step size in the previous formula to form estimates of the expected reward for all actions. The first example we saw, well, in fact, we saw first the second example, which was to form, to consider equally weighted rewards to form our estimates of the expected rewards. So this entails considering a time step of 1 over n, or we could consider a constant time step alpha, and this entailed putting exponentially more weight on more recent rewards. So these are two possible choices. There might be many other possible ways to select the time step. So uh, in the literature, there were necessary and sufficient conditions to ensure that were discovered to ensure that QT, our estimate of the expected reward of action A, is guaranteed to converge to the true expected reward for action A, Q star A. Okay, so these conditions are the following. So to ensure that your estimate will eventually converge to the true value, the following two criterias are needed in theory. Okay, so you need that the sum of all alpha A's is infinity, but the sum of all step size squared is finite. Okay, so you want to have that the sum of the absolute value is infinity, or the absolute time steps, but the sum of its squares is finite. So intuitively, what's the rationale behind these conditions? The first step is needed so that the algorithm can overcome any possible initial condition. Okay, so if your initial estimate is very, very, very bad, then you want to sufficiently move so that you will uh, remove the impact of your initial estimate and ultimately guarantee convergence, or be able to attain convergence to the true expected value. The second condition is needed to ensure that step sizes are eventually small enough so as to allow convergence. So if step sizes they remain too large, then you'll never be able to converge to the right point. You'll constantly fluctuate around the correct value. Okay, so to ensure that eventually you'll converge to the point, eventually step sizes they must not be too large. So this is why the second condition is needed. Okay, so these are theoretical conditions for estimates to converge to their true values, but in practice, are these conditions useful, and do people respect them in practice? Um, Okay, so the first part is just repeating what we just said. Okay, I'll answer what my question first and get back to that first part. Okay, so in practice, do people use step sizes that meet these criteria? And the answer is no. Okay, because the sequences of step sizes that guarantee convergence in practice they entail learning much too slowly. Okay, so they're used in theoretical work, but in applications and in empirical research, uh, step size sequences are typically don't typically meet the previous two conditions. Okay, because having, for example, the two previous conditions met in practice, it entails learning very slowly. So this is, although it guarantees convergence, people don't necessarily care to use them, and they are fine with using step size sequences which don't match these criteria. Okay, so one question we have to ask ourselves is the I'll go back one slide. The two schemes we've presented, do they meet these conditions? Okay, so clearly the equal weighting case does not meet the first condition. Okay, so if you sum alpha, a constant, from time 1 to infinity, of course this series will diverge. So in that case, you will never converge to the true value. You will continue, as mentioned, fluctuating around the true value, but you'll never exactly converge to it. Conversely, the equal weighting scheme matches these conditions. Okay, so it assures convergence, and this is true from the law of large numbers we've discussed earlier. So if you have ID random variables and you just take their sample average with equal weight, eventually that average will converge to the true expected value. Okay, so this is good for stationary problems. So um, if you have a stationary problems, then it makes sense to have equally weighted rewards to form your estimates, because it will converge to the true expected value. But if you have a non-stationary problem, then for non-stationary problem, you can never converge to an expected to the true expected value, because the true expected value keeps on changing. So in that case, it makes more sense to weight more heavily recent rewards and use an equally weighted scheme. Okay, so the methods we've discussed earlier, and I mean in particular the exponentially weighted scheme, they have estimates of actions value which are dependent on this. I wrote Q0A, but maybe I should have written Q1A. Okay, but so Q1A is the initial estimate of action reward expected rewards at time 0. So before any action was selected. Okay, so the current estimates of values of all actions are biased by these initial estimates. Okay, so if we go back to the few slides, if we go back to the equal weighting scheme, we have that our current estimate is the sum of exponentially weighted rewards. So the expectation of this term here, the expected reward is clearly the true expected reward. But here we have this term here, Q1A, which appears in that sequence. So we can see that if Q1A is different than Q star A, then this term will cause bias for the expected reward of action A. Okay, so we see that the initial estimate here of action A has an impact. For equally weighted rewards, let's go back a few steps here. So As soon as you sample an action A once, then the impact of your initial estimate Q1A will disappear. But if you never sampled from lever A, then your estimate is the initial estimate, so this also has an impact. Okay, so these two schemes, equally weighted and equally weighted rewards and constant step size, they both they both entail that the initial estimates have an impact on the current estimate for all actions. Okay, so for, as we mentioned, for the sample average method, when all rewards have an equal weight, the bias disappears as soon as the action A is sampled once, whereas for the constant step size, where rewards are exponentially weighted, the bias is always present. Okay, so the impact of the bias is exponentially decaying with time, but it's always present. Okay, because here, let's go back a few slides. In the exponential weighting scheme, the current estimate always depends on the initial estimate, but its weight decreases exponentially through time. Okay, so is this a good thing that we have bias for estimates of action values? Uh, well, you might think, okay, this is not a good outcome, but in practice, we can see that it's often not really a problem. Okay, so there's a downside to it, which is that initial estimates must be selected by the user. So they're somewhat subjective, um, and if you want to implement that, well, you could put them equal to 0, but uh, it's still a subjective choice, so you need to come up with initial estimates of action. But on the upside, they are an easy way to supply some prior knowledge about rewards levels. Okay, so if, for example, you have, before applying reinforcement learning, you already have an idea of the expected of rewards. It might be like a vague idea, it might not be precise, but you can use that prior knowledge to select initial estimates of the various actions. Okay, so it might be useful in that case. And furthermore, there's another positive outcome on uh, estimates of the various action values being dependent on the initial estimate. It's that it's possible to encourage exploration through suitable choices of these initial action values estimates. Okay, how do we do that to encourage exploration? This is done by putting over optimistic initial values for action values estimates. Okay, so let's say the expected rewards for all levers, they all revolve around 1, let's say. Then you could put initial estimates of 2 for all actions. Overly optimistic estimates. Okay, so what's going to work in that case? So um, whatever the action you take, then because your initial estimates are overly optimistic, then the expected rewards are like the expected rewards for all actions is lower than your initial estimate you've postulated. So the rewards, because their expectation is lower in average, their rewards will be lower than the average estimates you've put for all actions. So in that case, every time you sample an action, the learner, will tend to switch to other actions because they're always disappointed with the reward it's receiving. Okay, so the rewards always ends up being, or most of the time ends up being, lower than your initial estimate. So this will push down your estimates, and the user or the agent learning will tend to switch to all actions until he's disappointed with all actions. Okay, so this favors uh, exploring all actions at initial stages of the of a run or an experiment. Okay, so even if you're greedy and you always select the action with the highest estimate because you've were over optimistic about these estimates, every time you select an action, its estimate will tend to be pushed down and you will switch to other actions until you've explored most of all actions. Okay, so we can see that having to select initial estimates for actions is not necessarily a negative outcome, even if it entails having biased estimate, because you can use that to force exploration. Okay, so this approach might be useful, um, but a drawback associated with that is that it only forces exploration initially at initial time steps. Okay, because let's say you set up overly optimistic estimates for your estimated value of all actions, then at the initial stage, as we mentioned, the learner becomes disappointed with all actions and tries them all until he's disappointed by all of them. But after that, the expected rewards should be the estimate should eventually be stabilized around the true expected value for for all actions. However, if you have a non-stationary problem, the need for exploration is constant. So you don't need only to explore at the beginning, but because rewards are changing all the time, then you need to have some constant exploration. So in that case, having initial estimates that are overly optimistic is not a good solution because the latter only entails having more exploration at the beginning. But once your estimates have gone down to being around the true expected value levels, then you don't have excessive exploration. So in that case, for non-stationary problems, having initial estimates that are overly optimistic is not sufficient to ensure constant exploration. Okay, so you need to impose exploration through other means, like for example, an epsilon greedy policy or something like that. Okay, so we'll stop here for this video, and the next time we'll jump to other uh, ideas to propose policies. Okay, we've studied epsilon greedy policies, then we'll see other policies that can be applied, but please look at the third video of the chapter for that. So have a nice day.